for carrying the torch and for this their hard work on this workshop. So I'm very happy to introduce our next speaker. So it's Cosmin Pohoata, who's currently at the Institute for Advanced Study, but he will move to Emory in the fall, and he will talk about the permanent determinant problem. Okay, Cosmin, take it away, please.
Thank you very much, Sebi. Thank you, first of all, to all the organizers for having me to this wonderful workshop. It's been really fun. I apologize for not being around yesterday. I really missed out. Thank you for all the speakers for the nice talks earlier. They're super enjoyable. To begin, perhaps I should warn you that I don't really work in algorithms nor complexity. I'm not really working in computer science in general, per se. I work mostly in extremal combinatorics, discrete geometry, a bit of analytic number theory. But I do enjoy, however, every time a problem in CS is related to some things I know. So today, what I thought I would do is to tell you about one such problem. Perhaps it's a problem that most of you or some of you already heard about and know other things about. It's the so-called permanent determinant problem. I want to give you an outsider perspective on this problem that I really like and I think about every now and then with every occasion I have, and I'll try to raise some questions. So without further ado, let me maybe start and pose this problem. So the setup is quite simple. The two main players are the following. If I give you an n by n matrix A with entries, let's say in some ground field F, which you can think of as any field you want, you can talk about the determinant of the matrix A and the permanent of the matrix A. So the determinant, I'm sure everyone knows, is this alternating sum of products of n elements chosen from the matrix chosen from transversals in the matrix. So these are n elements where no two lie in the same row or the same column, and such transversals are naturally parameterized by permutations in the symmetric group of n elements. And this is an alternating sum where the sign in front of this product is the signature of this permutation. So already from this definition, you can see that the determinant has maybe relevance to combinatorics. It appears in a lot of algorithms problems, it also carries a lot of geometry, as we know. The permanent is very similarly defined. It's the same sum, except it's not an alternating sum at all. There's no -1 power in front of this product. So it has this almost the same definition except for this sign. And in some sense, it's even more natural of a parameter in combinatorics problems. For example, if you take a matrix that encodes the edges of a bipartite graph with n vertices on one side and n vertices on the other side, so a matrix with zeros and ones, whenever a vertex from one side is connected with a vertex on another side, so the rows and columns correspond to the vertices from the two sides. So the permanent of that matrix is really the number of perfect matchings of such a bipartite graph. For computational purposes, first, maybe before I get to that, trivial observation, if the field has characteristic two, these two parameters, the determinant and the permanent, are exactly the same notion. There's no minus sign. However, in general, for computational purposes, these two things tend to be quite different. So computing determinants is quite an easy problem in the sense that there are well-known polynomial time algorithms for computing the determinant of an n by n matrix. So standard Gaussian elimination gives you an algorithm that runs in cubic time. Strassen, in the very paper that introduced the subcubic algorithm for matrix multiplication, proved that you can also compute determinants in the same time that you can compute the product of two n by n matrices. In fact, the two problems are equivalent up to constants. So there are good polynomial type algorithms, even better than cubic. This W stands for the best known matrix multiplication exponent. On the other hand, computing permanent is hard, not just colloquially speaking. This was made formal by Valiant in the late 70s. Computing the permanent is a problem that's in Sharpie. It's Sharpie hard. In fact, I think for 0, 1 matrices, it's Sharpie complete. This was Also, the paper with Valiant introduced this complexity class to begin with. I won't really get into this at all. What one takeaway from that I want to mention is that it's a rather special problem in this this class of Sharpie hard problems because its decision counterpart is there are polynomial time algorithms for it. So for instance, there are well-known polynomial time algorithms to find the perfect matching in a bipartite graph with n vertices on the left and on the right, but computing how many there are is a difficult problem. The other takeaway is that generally problems that are Sharpie hard are generally believed to be more difficult than problems that are NP. So in particular, if you would have a polynomial time algorithm for computing the permanent of an n by n matrix, you would prove that P equals NP. So this is some background suggesting that there's a fundamental difference between determining these two parameters given n by n matrix. I want to share now a more quantitative perspective. Let me change a little bit notation. So instead of a matrix A, I'll use a matrix X that's n by n. Again, entries are from a ground field F. And suppose I give you the following scheme to compute the permanent of the matrix X. So suppose I would like to find a matrix Y of possibly larger dimensions. So this is an M by M matrix, where the permanent of the original matrix is equal with the determinant of the second matrix Y. And the entries of the matrix Y are linear forms in the variables of the matrix X. Okay, so each entry in the matrix Y, it's a linear function of the variables defining the matrix X. So you can hope to come up with a matrix Y with this property. And if you can come up with a rather small matrix Y, right, it seems like a good plausible scheme to maybe compute the permanent of X. If you could find, for instance, a matrix Y that has dimension M that's polynomial in N, well, then implicitly you would find a polynomial time algorithm to compute the permanent of X, because you know how to compute determinants very fast. Okay, that seems maybe too good to hope for, but the question, the quantitative question perhaps is a bit more accessible. So the question is, okay, suppose I have a matrix Y that satisfies these two properties. How large must M, its dimension, be in terms of N, the dimension of the original matrix? So this is the content of this so-called permanent determinant problem. I'll take a moment to pause if there are any questions. Also, I'll use this as an opportunity to mention that I don't really have you on my screen because I'm only using my laptop. So please feel free to interrupt me at any time. And also, please stop me after 25 minutes because I don't really have the time.
Do you have a small example for this? Like anything?
So I'll mention some things in the moment.
Okay.
So yeah, I should say the problem has a long and kind of fuzzy history. If you, in some sense, it goes back to a question of Polya from more than 100 years ago. So Polya noticed the following simple identity. If I give you a 2x2 matrix, of course, you can write the permanent of this 2x2 matrix as the determinant of another matrix 2x2, where indeed the entries are linear forms. The permanent of this is really the determinant of this, where you just put a minus b here instead of b here. And here the question, okay, can identities like this be extended to higher dimensions? And perhaps to give ourselves some convenience for later, let me introduce this notation. So this problem is usually stated in terms of what's called the determinantal complexity of the permanent. So given a natural number n, you can talk about the determinantal complexity of n over the ground field F that I omitted, I apologize, to be the smallest dimension M for which there is an M by N matrix Y satisfying the two properties. So the smallest dimension that you can find is the determinantal complexity of the permanent in the previous question.
So here you want equality in terms of polynomials. Identity
yes.
of polynomials.
Yes. So equality as so this is you should think of the entries of X as variables. You have the permanent is polynomial in these n squared variables, and the right-hand side is also polynomial in the same n squared variables. Any other questions? Okay, so let me tell you a little bit of history behind this problem. Sego immediately after Puli asked the question, the same year, plus minus one, I don't know how archive work more than 100 years ago. Sego showed that the determinant complexity is always at least n plus one for every n at least three. So in other words, you cannot really hope to find an identity like this, where if you start with an n by n matrix, you also write down an n by n matrix here. You must write a matrix that has dimension at least n plus one. This was improved later by several people. The ones I was able to trace, von Zur, Gatem, improved this n plus one to this better linear function in n, root 8/7 times n. Then independent works of Babai, Kai, Meshulam around the 90s showed root 2 times n. And this was the state of the art for a bit. Then Mignon and Resser in 2004 proved in a very beautiful paper, showed a lower bound of n squared over 2. And this, perhaps surprisingly, happens to be the best known bound for this problem. So I remind you, if one would be able to find a matrix Y that satisfies that equality with a dimension that's polynomial in n, then you would prove that P equals NP. So one should be able to show that this is at least super polynomial in n. And in fact, the folklore conjecture for this problem is that the determinantal complexity of the permanent should be at least exponential in n. However, the best known bound is this quadratic bound of Mignon and Resser from 2004. So I want to tell you today what's really the flavor of this argument, the main idea. It's quite simple. It's a rank argument, and the point is to consider the Haitian matrices of the corresponding polynomials from the left-hand side and the right-hand side. So I remind you, given if you think of the permanent of the matrix X on the left side as a polynomial in these n squared variables, the Haitian of this permanent is this n squared by n squared matrix, where in the rows and the columns are indexed by variables. So if you want, they're indexed by pairs, ij. And in row ij and column kl, you have this double derivative of the permanent. So you differentiate with respect to xij and differentiate with respect to xkl, the permanent. And you can do the same thing for the determinant of x. You can write down this Haitian matrix. There's also going to be a special concrete explicit matrix that will play an important role. Is this following matrix? It's an n by n matrix that has all ones except for the top left corner where you see 1 minus n. It's an explicit matrix that has two very important properties. So first property is that the permanent of this matrix is 0. This can be computed quite fast. For instance, you can compute permanent by expanding with respect to the first row, like you compute determinant, except you don't really have to put minus signs anywhere. So what you do is you have 1 minus n first times the determinant of an n minus 1 by n minus 1 matrix here. That's all ones. I don't even need to compute the permanent of this all one matrix here, because then when I do plus 1 times the corresponding n minus 1 by n minus 1 permanent, I also get the all one matrix, and I get it n minus 1 times, 1 time for each one here. So I have a 1 minus n times the permanent of the all one matrix plus n minus 1 times the permanent of the all one matrix. So that gives you a 0. These things cancel out. Perhaps the most important property that this matrix has, for which really the argument wouldn't really go through, is that if you compute the Haitian of the permanent and you evaluate this Haitian at this matrix A, this matrix that you obtain has full rank. So the Haitian of the permanent is this n squared by n squared matrix. The rank of this Haitian, when you evaluate it, when you insert x equals a, this concrete matrix here, you get a matrix that has full rank. This is a bit more delicate to verify. However, I hope you believe me, because it's a really explicit matrix. So you can really compute the entries of this Haitian. And in fact, I wrote down some formulas here. So if you take two derivatives of the permanent and you evaluate, you plug in x equals a, you get n-2 factorial if the corresponding indices I, j, k, l involve 1. So if for instance, if you have if one of these things is 1, then it's rather easy to compute the two derivatives, and essentially you're gonna just get an all 1 matrix that's n-2 by n-2, and the permanent of the all 1 matrix is the factorial. And when 1 is not part of the indices, you get -2 times n-3 factorial. Okay, so whatever you with this concrete Hessian matrix, you can compute its rank or check that the determinant is non-zero. Okay, so what do you do with these Hessians? It's really a the proof has at least the main idea has 2 lines in some sense. So you have this equation that you start with, the permanent of x, the n by n matrix, is equal to the determinant of this m by m matrix. And here I kind of did a translation of the coordinates. I want to use homogeneous linear form. So there's no constant term in these linear forms in the n square variables. So I subtracted by my matrix A. This is the explicit matrix A from before. And C here is a matrix of constants. Again, an m by m matrix of constants. So I can do this. And what's really nice about the Hessian is that it behaves quite well when you take linear changes of coordinates. So if you write down the Hessian of this permanent of x, well, and basically just differentiate this equation n squared times and put them all together, you get an equation that follows for the Hessian of x, of the permanent of x. You get some m squared by n squared matrix L, for which this Hessian is the transpose of L times the Hessian of the determinant of the matrix that you have inside here times L outside. Okay, so L is m squared n squared. This is an n squared. The dimension of this matrix on the right hand side, I want to emphasize, is n squared. Inside it's m squared by m squared, but then you multiply with this matrix L. That's quite explicit. It's the matrix that encodes the change of variables. The entries are this. You don't really need to worry too much about this. Of course, hopefully it's believable that such an equation exists. You can just prove it using chain rule, multivariate chain rule. Any questions about this? This is okay. With something like this in hand, all I want to do now is plug in this concrete matrix A from the start. So I know that if so the Hessian of the permanent evaluated at A is equal with this product of matrices. Here, this L matrix times, so this matrix here disappeared when I put in x equals A. So this is just 0. So here I just get the Hessian of the determinant value at this matrix of constants C twisted by this variable change matrix L. And I can apply rank. So this is a matrix equality. If I evaluate the ranks, so the rank of the matrix on the left-hand side is the rank of the Hessian evaluated A. Remember, this was n squared by design. That's how I chose this A. It's important. So the property that Mignon and Ressier had their eye on was a matrix that has the Hessian of the permanent with really high rank, as high as possible. It happened that they could find one with full rank. So they have here n squared, and the rank of this matrix here on the right hand side is at most the rank of this m squared by m squared matrix that's inside. L only possibly decreases the rank. So you have this rank upper bound, and then the argument ends by noticing that this Hessian of the determinant of C has rank at most 2m. So this is an m squared by m squared matrix of constants. And if you can show that this rank is at most 2m, combined with the other side of the inequality, you get this m is at least n squared over 2. And this, I won't really get too much into it. I just wanted to add some lines to suggest that it's really an explicit calculation. So it's a matrix of constants from the first property, although, as I said, maybe I suggested briefly, the first property is not really that important, but it's convenient. So since this explicit matrix A has 0 permanent, when you plug in A in the original equation, so this thing disappears, you get a determinant of C is 0, so C doesn't have full rank. After doing some elementary row column operations, you can take C to have this form where S is strictly less than M. It takes some technical linear algebra trick to note this, that actually you can assume with a lot of generality that C has this form in this equation. So not only that you can, after row and column operations, you can reduce it to this form separately because it doesn't have full rank, but you can also take it to have this form in this equation. This is an easy exercise. And then also you can assume that S is actually m minus 1. So not that just it has rank smaller than m, but it has in fact rank m minus 1, because it's easy to compute explicitly the Hessian of the determinant when the matrix C has less, at most m minus 2 ones here. In fact, most of the entries here are 0. So the rank in this case will actually be dramatically smaller than 2m. So the kind of the interesting case is when S is equal to m minus 1, and this is a calculation. So C is almost this diagonal matrix with a 0 in the corner. So this is their argument. I want to tell you kind of a slightly different perspective that invites maybe some avenues. Here's another way to think about this proof. So you have this equation, and now I just assumed from the get-go that these linear forms are homogeneous, so they don't have any constant terms, and this matrix C of constants is just this diagonal matrix, almost identity matrix with all ones except for the top left. Okay, so ones everywhere, +1, L22 has a +1, L33 has a +1, LMM has a +1. Everything else, they're just homogeneous linear forms and in the n square variables, x1, 1, 1, up to x and the variables defining x. And A is the concrete matrix from before. So what is this argument doing? This argument is implicitly looking at the coefficients of the quadratic terms in this polynomial equality. So as Elena said, this is a polynomial equality between two polynomials and n square variables. And I claim this argument is just looking at the quadratic terms. So here's a question: what's the coefficient of some quadratic term in this left-hand side? So of this permanent on the left, it should, if you expand out the formula for the permanent, it should just be some coefficient that depends on the matrix A that we shifted by. Okay. So there are all these aij's floating around in the product of the n elements involving that transverse. So expand that out, you get you get some coefficient that just depends on the entries of A. However, let's look at the coefficient on the right-hand side. So these are linear forms, and I can try to think, okay, what are the contributions that to this monomial? So when do I see an xij times xkl? So I go, let's say I expand the determinant by the first row again. So I look at x11. It has some xij. If it doesn't, okay, ignore. But let's say it has some xij term in it. The coefficient there is non-zero. Then I have to look, when I expand this thing out, where do I pick up xkl from the n-1 by n-1 determinant here? Well, it's not difficult to see that you only pick it up from L22, the xkl term from L22. You don't really pick it up from anywhere else. And it's really because of this +1. Same, you pick it up from L33 and LMM. Okay, where else do you see xij, xkl? Well, you can still see it from L11 if you just focus on the contribution of xkl. Xkl can appear in the linear form L11. In this case, I have to see where do I pick up xij from here. Again, I pick it up only from the diagonal, from L22, L33, LMM. I wrote here a formula. I explained maybe the first two. There are some other ones. I didn't stop with my expansion of the determinant after the first row. I also have to look at the contribution of L12. So I have to ask, okay, where is Xij? So I might have some Xij in here, or where does it pick up on XKL? So I have to ignore the column. I have to ignore the row it's in. I look at the remaining n-1 by n-1 determinant. I claim L12 only gets an XKL from L21. L13 only gets an XKL from L31, and so on and so forth. L1M only gets an XKL from LM1. And vice versa, if you look at the XKL term from L12 in this determinant expansion, you want to ask where does it pick up on Xij? Again, I claim it only picks it up from L21. So this takes, it's kind of hard, probably hard to follow live. It's not difficult if you stare at it a bit yourself. I put the picture with a 3x3 to also maybe clarify a little bit the sign here. So notice that all these terms here have a minus sign in front. It's not really important at all for the argument. But see, for instance, what I was saying here, when I look at the Xij contribution, let's say from L12, I have to look at what does it get multiply the term Xij with from the remaining 2x2 determinant. The 2x2 determinant, if I cross out this column and this row, it's this one. Okay, and I have to ask, where do I see Xij times XKL? Just this degree 2 term. I don't care about degree 3 or more. So the claim was that it only comes from L21, right? Because when I write down the formula for this 2x2 determinant, I do this product minus this product. Notice that L21 is the only thing that gets multiplied with this plus 1. So it only is the only term that involves linear terms left. And so it's really the only one that can contribute a single XKL to this L12. So that's kind of the analysis that you do. And notice that it has this, this minus sign. Okay, any questions about this?
My question is, so what you are trying to find the L's, the linear forms, or like a set of linear forms that is nice or something?
I'm doing this kind of horrendous operation of I have this polynomial and n-square variables on the left. I'm interested in the degree 2 terms. So degree 2 terms are monomials of this form, Xij times XKL. They have some coefficients on the left. They depend on this matrix A.
Sure.
Now I can try, I'm trying to understand how they look like in terms of the right-hand side. So this right-hand side is a determinant with linear forms inside. And I'm asking, okay, what are the degree 2 terms that come out when I expand this determinant brutally from the first row? I get something like this.
Sure. And then, like, what is the point?
So the point is that this Haitian kind of rises naturally. What is the main observation? The main observation is that so this is the coefficient of this Xij XKL term. We can write it as the sum from t equals to up to m of these products of linear forms. This, if you stare at it closely, it kind of begs to be encoded as a sum of inner products. So this is really the inner product between these two vectors, Aij, BKL, where Aij is really the m-1 dimensional vector that has all these coordinates. So in particular, this one has all coordinates equal to L11 Ij. This BKL is the vector that has all these coordinates as I vary t from t equals 2 to m. So it's this vector. So this is just a sum of four inner products, which means really that we have an understanding of these coefficients. These coefficients of Xij XKL from this is secretly really the Haitian. That's kind of how the Haitian appears, perhaps more explicitly. So this, if you organize these coefficients in a matrix, so it happens to be really the Haitian matrix from before. Computing the coefficients of the quadratic term is really the same thing as taking these double derivatives. And we have this equality for the term so that we know what the entries are. it's really the sum of these four inner products. So it's really, we got an expression for this Hessian matrix of the permanent as a sum of 4 gram-like matrices. So it's there are 4 matrices with dimension n-1 and n squared, and they're quite special. So A was really this matrix consisting of these vectors Aij, and remember Aij is really it's a scalar multiple of the all 1 vector with n-1 coordinates. B is really this matrix obtained by stacking the BKL vectors together, and so on. C is the matrix obtained by stacking the C vectors, D the B vectors. And I can apply rank. So the rank of this matrix is n squared, the Hessian, the matrix here was chosen for this so that this has full rank. These have rank at most 1 because A has rank 1. Remember, A is quite special. And the other ones have rank at most n-1. So this gives you this n squared is at most 2m. So this leads to some natural questions. Let me see how am I doing with time. Oh, I'm out of time. I'm sorry. Okay. I was hoping someone would stop me. So just some quick observation. It's kind of the point of this alternative perspective was to emphasize that this Mignon-Resser argument only looks at degree 2 terms in this original equation. So we can ask, what about degree 3 terms? What happens if you compare coefficients of degree 3 terms? This is a question that makes perfect sense. You can perhaps try to organize these coefficients instead of a matrix in a 3-dimensional tensor, let's say for degree 3 terms. So it's kind of like a Hessian tensor, and I can try to look for some notion of rank that allows me to adapt this argument. It would have to be a rank notion that kind of respects this implication that if you have an equality like this of tensors, the rank kind of is well behaved. The effect of this tensor L is the same. It can only decrease the rank. And such rank notions exist. So they've been introduced recently by Tao in the context of the capset problem. So this is like the slice rank. There's a geometric rank introduced by Koparty, Moshkovitz, Idam. There's some other ones motivated by higher order Fourier analysis, analytic rank. All these kind of ranks satisfy this, and you can hope you can try to run this argument. And in fact, I tried. However, turns out this only leads to the same kind of quadratic bound. So you can reprove really that m is at least n squared using this. In fact, for any k at least 2, if I look at the coefficients of degree k in this equation, this argument can only lead to an equality of the form m is at least n squared, where the constant now depends on k. I circled it because sadly I couldn't really do a good job computing it myself. If anyone could help me, I would be very happy. I suspect that maybe for larger k, the constant could maybe get better than 1/2, because there are just more monomials of degree k that you have in the permanent than degree 2. It seems sensible that if you take k to grow with n, that maybe that has this rank argument, higher dimensional rank argument has more information. However, I was not really able to prove this. I was able to prove something when the underlying field is the set of reals. So using a slightly different argument inspired by the slice rank developments, in particular some crude Left-Pak lemma further developed by myself and Fedor Petrov for a different problem in discrete geometry. We can prove that m is at least n-1 squared plus 1 if the matrix has real entries. Essentially, it's really running the quadratic argument, but not with rank. You look at positive and negative inertia indices and compare those. I won't say more. We can ask, okay, what, maybe this one I won't really get into because in the interest of time. So you can ask maybe about this relaxation of the permanent determinant problem. What if I look at the matrix Y, where the entries are not linear forms of the coordinates from X, but they're polynomial maps of some degree at most D, where D is some fixed number, that's at least 1. In particular, where D is 1, these are linear forms, is the permanent determinant problem. Can you prove something using this kind of higher dimensional results? Last night when preparing these slides, I was able to write something. So one can show that one can generalize this argument. So essentially look at degree 2D terms and use higher dimensional ranks and show that m is at least n to the power 2 over d. So this when d equals 1 recovers the minion-Russell argument, but in higher dimension it gets worse and worse. I put this between quotes because, as I said, it's from last night, so take it with a huge grain of salt. It could be completely nonsense. Yeah, it's kind of a disappointing result because this bound is worse than n, worse than linear when d is at least 3. Perhaps I'll leave you with a question that seems that so far I didn't really see it anywhere in literature, but maybe it must be somewhere. So in light, I guess, of the second perspective, it seems like very reasonable to ask, well, how do you actually incorporate the data of all the coefficients, not just of a fixed degree k? What if you look at the terms of degree at most k? So look at degree 1 term, degree 2 term, degree 3, stop at degree 10. How do you encode the information of all the coefficients? Suppose you have the permanent of x plus a and the determinant of y agreeing all the way up to degree k. Can you prove that m is at least n to the k if you somehow use all that equality? So far, all these arguments only use the equality for a fixed degree. And then the last question is really about what specifically about the permanent are we using? If we think about the permanent of a matrix as a function of the column vectors of the matrix, the two crucial properties of the permanent is that it's symmetric. So unlike the determinant, if you swap two columns and you compute the determinant, if you compute the permanent, you get the same thing. And it's multilinear. So what happens if you replace the permanent with another multilinear symmetric forms? So like if you replace it with this generalized inner product of the columns, turns out you cannot really improve on the quadratic bound. I was afraid to write this because I feel like I proved it a while ago, but I couldn't remember the proof last night. So I claim with again, a grain of salt that if you replace permanent with this, you cannot really improve on n squared. There is always a matrix with the dimensions n squared by n squared, whose determinant equals this expression, starting with an n by n matrix x. More generally, people have been really interested also in, so forget about the permanent completely. You can ask for any polynomial in n variables. What is the determinantal complexity of this polynomial? So what is really the smallest dimension of a matrix for which this polynomial is really the determinant of some matrix in those n variables whose entries are linear forms. And in the case of the permanent, so the permanent was a polynomial in n squared variables. The minion-Russell argument gave a linear bound in terms of number of variables. So the determinant complexity of the permanent was n over 2. The question that's also wide open, very surprisingly, I think, can you prove a superlinear bound for the determinant complexity, not just for the permanent, for any polynomial of your choice? So just choose any polynomial. There is no known explicit example of a polynomial for which you can actually prove concretely that the determinant complexity is superlinear. So that's all I had. Sorry for keeping you over time. I'm very sorry.
It's okay. Thank you. Thank you, Cosmin. So yeah, maybe we can hold on the questions if people want to chat afterwards. So thank you.